Let me share my screen. During this lecture, we will finish our program from yesterday, when we looked at flows of solutions to stochastic differential equations, and also we will introduce the notion of a random dynamical system, and look how it relates to the flow of solutions of stochastic differential equation. Okay, so I will remind that we considered the stochastic differential equation 3 of the form dxt equals axt dt plus bxt dwt, where a and b are Lipschitz functions, and w is a Brownian motion. And we proved that for every initial condition that x at time s equals to x small, there is a unique solution up to indistinguishability. Indistinguishability means that if we consider two solutions to this equation, then with probability 1, two solutions coincide for all t. Okay, and we denote the solution that corresponds to initial data Sx by phi st of x. So for each s and x, phi is a continuous process in t. Okay, now I'm sorry, 1 second. Yes, I'm sorry. So, last time we formulated our aim to find a modification of solutions phi that constitute a flow of solutions. That is, we want to find a modification of phi stx that are linked by the flow property, means that the composition of mappings phi rs and phi st equals to phi rt, and also as it was in the case of ordinary differential equations, we want each phi st to be a homeomorphism of rd. Okay, so now let's proceed with this task. To find a modification of the process phi, we will use Kolmogorov's theorem. So let me remind it. Assume that we have a process xi indexed by a d-dimensional cube. So once we can find positive constants gamma, c, and epsilon, such that expectation of the increment of the process to the power gamma is bounded by the constant times the increment of arguments t and s into the power bigger than d. Then if we can find this such estimate, the process has a continuous modification. Okay, so now our process phi is indexed by st and x, where x is d-dimensional. So we will look for estimates in which increments of x, s, and t will be in the power bigger than d plus 2. So here, a little difference with the Kolmogorov's theorem is that in ST, we have a process defined not on the cube, but in the region where s less than t, which is here. However, this region can be written as a union of a countable number of cubes. Okay, so once we have the estimate from Kolmogorov's theorem, the process will have a continuous modification. Okay, and the estimate we need is formulated in theorem 2, which says that for any p bigger than 1, there is a constant such that the increment of our process into the power 2p is bounded by this constant. Then we have the increment of x into the power 2p, and also we have increments of t and s into the power p. We will need this multiple later, but for the question of continuous modification, we can always look at st and x in bounded sets. Yeah, so when x prime are from bounded set, we can also estimate this bracket by some constant. So we will have an estimate from Kolmogorov's theorem with the power p. Yeah, and since p can be an arbitrary number bigger than 1, we can take, for example, p bigger than d plus 2. So we will get a continuous modification. And also in all considerations connected with this result, we will assume that s and t are also belong to the to some segment from minus c to c. Okay, so now let's discuss the proof of the estimate. The first result I will show is that the expectation of the norm of the solution squared, actually this is this is expectation of the norm in the power 2p. However, in this lemma, p can be arbitrary numbers. For example, p can be a negative. So we write expectation 1 plus norm squared to the power p. And it turns out that this expectation is bounded by the constant times 1 plus x squared into the power p, which corresponds to t equals s. The constant depends on p. Also, it depends on this c small, but it will be always the case with such estimates. So we will prove this lemma using the Ito lemma. applied to functions, applied to the function f capital of x. So here f small is 1 plus norm squared, so f small is 1 plus x1 squared plus xd squared. Yes, and then we take it to the power p. So this is our f of x. And we will substitute phi, the process phi into the function f. And since phi solves the stochastic differential equation, each component of phi is written as x plus the integral of a of phi dr and plus the stochastic integral. Here is aj, then here is bj, phi sr of x dwr. Okay, and according to the Ito lemma, to represent f as the combination of integrals, we need to compute first two partial derivatives of f. So here they are computed. The derivative of f in xi equals to p f of x to the power p minus 1 and times 2xi. Okay. The second partial derivative, okay, when we differentiate 2 times in I, we get the summed 2p f of x power p minus 1. And again, when we differentiate this f of x, we get 2 pi p minus 1 f of x to the power p minus 2 and 2xi squared. When I is not equal to j, we just don't have this summoned, and we get an expression of this form. It means that we can write that the second derivative of x is equal to 2 pi f of x to the power p minus 2. Yes, if I is equal to j, we get additionally f of x. And also we get 2p minus 1 xi xj. Here, delta ij is 1 if I is equal to j and 0 if not. Okay, so now all the derivatives are computed and we get the following expression. I is f of x, which is the value when t is equal to s. Yes, so this is f of x plus the integral with respect to dr will be the integral of the partial derivative of f, yes, times this coefficient a of phi. In other words, we get the scalar product of phi and a of phi. The same type of the integral, but the stochastic integral we get here. Again, this is the partial derivative of f times the scalar product of phi and b dwr. And one more term in the Ito lemma is 1/2 the sum of I and j, the integral of second derivative of f, which is here. Okay. Then it is integrated with respect to the product bi bj times the quadratic variation of the Brownian motion, which is just dr. So we get this representation. I remind that we're interested in the expectation of this variable. So let's take expectations. When we take expectation, it appears here, here, and the expectation of the stochastic integral is it is equal to 0, because now the stochastic integral is a martingale. It is a martingale because I recall that we constructed a solution which was integrable in all powers p. So we proved that solution exists, and the solution is such that all such expectations are finite. So hence the stochastic integral is a martingale, and after taking expectation, it disappears. Now we can estimate the right-hand side by noting that absolute value of x, of course, it is less than f of x to the power 1/2. Yes, because f of x is 1 plus x squared. Also, a is Lipschitz, so a of x, it can be estimated as some constant 1 plus absolute value of x. Okay, and this is also can be estimated as some other constant times f of x to the power 1/2. It means that this expression it can be estimated as some constant. Yes, we have f of phi to the power p minus 1. The scalar product we estimate as norm of phi times norm of a of phi. But both these norms are estimated as f of phi to the power 1/2 with some constant. So it is this is estimated as f of phi to the power p, which is exactly f capital of phi. And in the last integral, the function b is also Lipschitz, so this is bounded by a constant times f of phi. Yes, when I is equal to j, we get one more f of phi. Yes, and here we have f of phi to the power p minus 2. So it will also combine into f of phi to the power p. And here, again, we have a product of phi and phi, which is less than f of phi. So all expressions under integral are bounded by some constant times this function. That is, we have the following estimate, and it remains to apply the Gronwall inequality to deduce that this expectation is bounded by the factor exponent times f of x times this one, which is exactly what we wanted to show. Okay, so we obtained some estimate on the expectation of the norm of the solution phi. Now let's apply this result to get another estimate. Lemma 2 states that for any constant p bigger than 1, the increment of the process phi in the variable t is estimated by a constant times 1 plus x squared to the power p and times the increment of t to the power p. To show this, well, assume that t prime is less than t, then we can write this increment phi stx minus phi s t prime of x as the sum of two integrals from t prime to t. Yes, the first is the integral of a dr, the second is integral of b dwr. So now let's estimate expectation of these integrals into the power 2p. So expectation of the integral of a in the power 2p, we estimated first we use Hölder inequality. To put 2p inside the integral, and this gives us t minus t prime in the power 2p minus 1. Yes, and times the integral, and we will have under the integral, we will have expectation of the absolute value a of phi s r of x in the power 2p. Again, we use the Lipschitz property of a and bound this by some constant times 1 plus phi squared into the power p, and we already know the estimate of this. Yes, in lemma 1 we estimated such expectation by 1 plus x squared into the power p. So we get an estimate of the form t minus t prime in the power 2p times 1 plus x squared in the power p. This is actually even better than we wrote here. Now let's look at the stochastic integral. So expectation of the stochastic integral in the power 2p is estimated. First, we use the Borg-Hölder inequality. Power 2p is estimated by the universal constant that depends on p times expectation of the quadratic variation of the martingale in the power p over 2, 2p over 2. The quadratic variation is equal to the integral of b squared. So we get an estimate like expectation integral of b squared in the power p. And now we do the same as with the first integral. We put p inside, which gives us additional factor t minus t prime in the power p minus 1. And under the integral, we obtain b to the power 2p, use the Lipschitz property of b, and use the estimate that we already know. And here we get an estimate of the type x to the power 2p and t minus t prime in the power p. So both these estimates give us the result in the lemma 2. Okay, so this was an estimate of the increment in t. Now let's look at the increment in s, in x. Lemma 3 is a sigma 1, but here we have expectation of the increment of the process phi in s and x, okay, squared. We add epsilon, which is an arbitrary positive number, and look at this expectation in the power p. So here p can be arbitrary real number. And the estimate is that this is less than a constant times the same expectation when t is equal to s prime. Yes, so expectation epsilon plus phi s prime of x minus x prime into the power p. Interestingly, this constant will not depend on epsilon. The proof is similar to lemma 1. Now consider the function f of x, which is equal to epsilon plus x squared. F capital is f small to the power p, and we will substitute this process eta t into the function f. Now eta t is a process defined for t greater or equal to s prime, and let's write the representation of eta in terms of integrals. So eta t is equal to phi s prime of x minus x prime plus the integral from s prime to t. The process phi of x will give us a of phi s r of x, and the process phi of x prime will give us a phi s prime r of x prime, and this is dr. Okay, and also we will have the stochastic integral, which is integral from s prime to t, b phi r of x minus b phi s prime r of x prime. And this is dwr. We already saw how to compute the derivatives of f. So we will get the following equality. So f of eta t is equal to f of eta s prime, which is exactly the phi s prime of x minus x prime squared plus epsilon into the power p. Okay, and this comes from the derivative of f. Yes, this term also comes from the derivative of f, and this term is exactly the second derivative of f. Now we take expectations, stochastic integral vanishes, and we do the same estimations as in the lemma 1. So this eta is bounded by f of eta in the power 1/2. Note that by the Lipschitz property, the increment of a is bounded by a constant times eta, yes, which is less than the constant than the constant times f of eta to the power 1/2. So in the integral, in the first integral, we will get again the bound a constant f of eta r, and the same bound we will have in the last integral. Okay, and also know that this constant is independent of epsilon. So we find that expectation f of eta is less than expectation f of eta s prime plus the constant times this integral. And again, we apply the Gronwall inequality to get actually what we need. As a consequence of this result, if we put s s prime equals to s, we get the bound that expectation plus the increment of the solution in x is bounded by increment of x. Okay. And now we are ready to prove the theorem 2. So in this theorem, we need to estimate expectation of phi st of x minus phi s prime t prime of x prime in the power 2p. And first we will compare both these variables with phi s prime t of x prime. So by the lemma 3, when we take epsilon to 0, we get an estimate that the expectation of this increment in the power 2p is less than a constant times this expectation in the power 2p. Again, this is bounded by increment of x in the power p and times this expression. Now recall lemma 2, that expectation phi st of x minus phi st prime of x in the power 2p was bounded by 1 plus x squared in the power p times t minus t prime in the power. And we apply this lemma with equals to s and t equals to s prime. This gives us precisely the bound for this quantity, and the bound is 1 plus x squared to the power p, s minus s prime to the power p. Okay, so we get the first estimate, and the second estimate is to compare phi s prime t prime x prime with phi s prime tx prime. And this is done again in the lemma 2. So we get a bound 1 plus x prime squared in the power p, t minus t prime in the power p. So the theorem is proved. As mentioned, if we take p bigger than d, actually it's not correct. P must be bigger than d plus 2. Yes. Then we deduce that our family of solutions of SDE has a continuous modification. I will denote this modification by, again, by phi. Now, modification is defined for s less than t, but I propose it as an exercise to show that this modification at every point sx has a limit when t goes to s, and this limit is equal to x. And a hint for this exercise is to make use of this estimate. Of the estimate from the lemma 2. Actually, in the proof of Kolmogorov's theorem, the main step is to get some uniform estimate on the supremum of such ratios from estimates of this type. So this can be done here, and as a result, we will deduce that limits when t goes to s exist and equal to x. Another interesting observation is in lemma 3, we wrote such estimate phi stx minus phi sty in the power 2p less than a constant x minus y in the power 2p. And in this estimate, p can be negative. It means that if x is not equal to y and p is negative, then this norm is integrable in the negative power. This means that the norm is almost surely not zero, which means that phi stx is not equal to phi sty. This is very close to one-to-one property. Well, it is not very close to one-to-one property. At least it shows that for different x and y, images will be almost surely different. We want more. We want to say that with probability 1, the mapping phi will be one-to-one. So we want the exceptional set when these variables can coincide. We want this exceptional set to be independent from x and y and s and t. And to do this, we will look at the process eta. So this process is the inverse of the norm of the difference of phi. It is a process in s, t, x, and y. Well, again, when s is not equal to t and x is not equal to y. What we will prove? We will prove that this process has a continuous modification. And since this process has a continuous modification, since phi is continuous itself, it will follow that phi is injective in X. Moreover, it is injective in X for all S and T. Okay. We already know the method of proving this. We will prove again some estimate of the increment of eta in the power 2p. Now eta is indexed by st, x, and y, so it is indexed by an argument of dimension 2d plus 2. So in from lemma, we will take p bigger than d plus 2 and deduce that eta is continuous in st, x, and y. The increment we will first we will take the increment in arguments such that st belong to the segment from minus c to c, and x and y are separated by distance at least delta. So x prime, y prime are also separated, and we will prove that expectation of the increment in the power 2p less than a constant times delta minus 4p. Okay, here is increment of x, increment of y, and increment of t and s. Okay. To do this, let's rewrite the increment of eta in the following way. Actually, the increment of eta is 1 over phi stx minus phi sty absolute value minus 1 phi s prime t prime x prime minus phi s prime t prime y prime absolute value, everything into the power 2p. So we take denominators outside. This gives us these two quantities, and in the numerator we use a triangle inequality, which gives us these two summands with an additional factor. Now we can take expectation, use Hölder inequality to separate expectation of eta stxy, expectation of eta s prime t prime x prime y prime, and expectation increment of phi between x and x prime and x prime. Now we know how to estimate all these quantities because of previous lemma, so I will write the answer. The answer is here we have the estimate x minus y, yes, to the power minus 2p, because eta is 1 over the increment of phi. Since x minus y are separated by the delta, this is less than delta to the power minus 2p. This is also less than delta to the power minus 2p, which gives us this factor. Okay, and what is in the brackets? This is again, this is the direct consequence of theorem 2. So as a result, the process eta has a continuous modification in the region minus c, less than s, less than t, less than c, x minus y greater or equal to the delta. Now we can take delta to 0, c to infinity, and deduce that eta has a continuous modification. As a result, with probability 1, all mappings phi are injective. Now let's prove that they are surjective. So we will do this considering the process eta, which is equal to 1 of the absolute value of phi evaluated at the inverse point x. So we evaluate phi at the point x over norm of x squared. So this transformation, in a sense, it sends infinity to 0 and 0 to infinity. So by considering properties of eta, we will prove that phi goes to infinity as norm of x goes to infinity. And the aim is to show again that eta has a continuous modification in st and x. And this is done using the estimate that the increment of eta in the power 2p in expectation is bounded by increment of x times increment of t and s times some multiple which can be bounded when we consider x from a bounded set. So let's look at this estimate. It's again, it is very similar to lemma 4. However, here we can have the case when x is equal to 0. In this case, we just estimate expectation of eta in the power 2p. This is expectation of 1 plus absolute value of phi, yes, in the power minus 2p. And we know how to estimate this expectation. So it's a constant times the norm of the argument, which is 1 over x, yes, in the power minus p. But this is less than constant times norm of x in the power 2p. And the increment of eta is estimated similarly to the lemma 4. So first we do some simple transformation, then use Holder inequality. We know how to estimate this quantity, and this quantity is estimated in theorem 2. We get the product of x and x prime. This comes from the estimates of eta. And the bracket is the estimate of the increment of phi. Now what remains is to put these factors inside. And we will get the right estimate, which shows that eta has a continuous modification, which means that the process phi tends to infinity as soon as the norm of x tends to infinity. In other words, if we add like a point infinity to Rd, then we can continuously extend phi to the mapping of the so-called compactified Euclidean space. Okay, when we add one point to RD, it's in a sense we wrap RD into a sphere. So mappings phi can be extended to a sphere, to the mappings of sphere, and in fact, these mappings are continuous in S, T, and X. In particular, they are continuous in T and X. When T is equal to S, we get just identity mapping. So we can continuously deform identity mapping of a sphere into the mapping phi st from the flow. There is a result from homotopic theory that mappings of the sphere that are homotopic to identity, they must be surjective mappings. So phi is surjective on a sphere, since phi sends infinity to infinity. Actually, phi is a bijection of RD, and since sphere is compact, phi is a homeomorphism of sphere. So we deduce that our mappings phi are homeomorphisms of RD. As we discussed yesterday, uniqueness of solutions imply that this equality holds for all T, almost surely for all R, S, and X. But since we have continuity, we deduce that the flow property holds for all R, S, T, and X. And the consequence, we proved that to the stochastic differential equation of this form, there corresponds a stochastic flow of homeomorphisms, which is a continuous process of solutions of the equation that are homeomorphic in X and form a flow in this sense. Moreover, by construction, phi st is measurable with respect to the sigma field generated by increments of Brownian motion from S to T. Hence, on the disjoint intervals of time, mappings phi act independently. And as another exercise, I propose to show that the distribution of these mappings is invariant with respect to the shift in time. In fact, this will follow from the stationarity of increments of the Brownian motion. Well, let's discuss this property in a more detail that will lead us to the notion of a random dynamical system. Let's fix some number v and consider a shift of the Brownian motion by v. This is the equation which is solved by phi. And let's, in both integrals, change variables by shifting to v. Yes, so we will get the integral from s minus v to t minus v of this function. Yes, so here we shifted r by v, and in the stochastic integral, let's also shift the bounds, but integrate with respect to the shifted Brownian motion. The shifted Brownian motion, it is again a Brownian motion, which means that this process solves the equation driven by the different Brownian motion. By the uniqueness of solutions, we can deduce that the shifted process phi constructed by the Brownian motion W is indistinguishable from this process constructed by the shifted Brownian motion W. And this gives us something more than just a flow property. We get, in some sense, we add the dynamics of the noise into this picture. So as times go by, the noise that drives the equation changes, and the process phi is just the same process, but evaluated at the changed noise. Because if we have equality of these random variables for all s, t, and v, then we can, for example, take v equals to s and say that phi s plus v of x, it is the same as phi s plus t, yes, is the same as phi 0t of x, but evaluated on the shifted Brownian motion. And this shift is usually denoted by theta. The mappings with this property are known as random dynamical systems. So let me give the definition. In this definition, X will be a measurable space. So first, let us define a metric dynamical system. A metric dynamical system is a probability space, and the group of mappings, so each mapping theta acts on the probability space. These mappings are measurable and preserve the probability measure. So the image of probability measure P and the mapping theta is equal to P, and usually theta is called the shift. So it is a group in the sense that the composition of two shifts is the shift by H1 plus H2. So this is a metric dynamical system. Now, if we have a measurable mapping of time, a random element omega, and x into x, that satisfies the following property. Then we say that we have a random dynamical system. Once we have such an equality for all s, t, and x, then we have a random dynamical system, because we have the flow property. So phi 0t x theta s omega, if we compose it with phi 0s omega, yes, then we will have exactly the composition of two mappings from the flow, which is phi 0t plus s of omega. So when we have a flow of mappings with this equality, then we get a random dynamical system. In the case of stochastic differential equations, we do not have exactly this equality. We have it almost surely when the exceptional set can depend on S. Such mappings are called crude cocycles. Okay, when this equality is true without exceptions, it's called the perfect cocycle property. And this point of view can be also described as follows. So we have a family of mappings phi that are indexed by time and omega, and so each realization of omega produces us with one mapping eta t, with one mapping phi t. However, when the time, let's say when s moments of time have passed, our noise omega shifted to theta s of omega. So at time s, we choose this mapping. At time t, we choose this mapping, but with respect to the shifted noise. And their composition is the same as the mapping at time t plus s, which is defined by omega. So conversely, when we have a perfect cocycle, we get a flow of mappings. It is defined by the cocycle x from time t minus s, but with respect to the shifted noise. And this is easy to check that indeed we have a flow of mappings. The importance of random dynamical systems is that when we have a random dynamical system, it can be lifted to the usual dynamical system, but on the product omega x. And this lift is given by the mapping that sends omega into theta t of omega and x into phi t omega x. Then theta t is a usual one-sided dynamical system in the sense that the composition of two mappings is equal to theta s plus t. Okay, and this fact allows to bring dynamical systems into the study of flows, of stochastic flows, in particular to use ergodic theory for dynamical systems to the study of flows. For example, the invariant measure of a random dynamical system is just the invariant measure for the dynamical system on the product. Okay, so next time we will look at some examples of random dynamical systems in the context of stochastic differential equations. We will prove the existence of random dynamical systems for stochastic differential equations. And we will also look at stochastic flows that are not generated by stochastic differential equations and discuss some methods how to work with them. And I think that's all for today. Thank you for the attention.
Thank you. Maybe some of the participants have questions, comments.
Well, I have the same question about the slides, how to get them.
How to get what?
The slides.
Ah, I can send. I will send it to Kate. Okay.
Okay, thank you.
Sorry if there are no other questions, then let's have a break for 25 minutes and we will continue with the lecture of Andrei Taragovtsov. So please join our next lecture.
Верните слайды на минуту.